We've been looking at continuity, we've been looking at differentiation. Now I'm going to talk through a theorem that brings these two together. Now obviously you must be comfortable with what a function being continuous means and what differentiation refers to. So let's take a look at this theorem that brings these two concepts together. If I've got a function, f of x, and a number a is in its domain, if f of x is differentiable at a, then f is continuous at a. So this function tells me that if I know a function, or this theorem tells me, if I know a function is differentiable at the point, then it has to be continuous. So that's what we're going to prove, and then we're going to look at how we can use this theorem and what else it stands for. So let's look at the proof of this theorem. So we're given f of x is differentiable at a. Okay, given that, so then we can conclude that f's derivative of a in the point a exists. And if it exists, then we know that f's derivative in the point a is the limit as x approaches a of f of x minus f of a over x minus a. That's one of the definitions of the derivative. So since the derivative exists, this is true. Now, what do we want to show? We know f is differentiable. We want to show f is continuous. So you need to know the definition of continuity. So we want to show that the limit as x approaches a of f of x is equal to f of a. So that's what we're trying to show, because that is continuity. So let's take a look. Let's start with the limit as x approaches a of f of x. That's the same as the limit as x approaches a of. Now, we're using a little trick here to get us to where we want to go. F of x minus f of a plus f of a. All right, a is in the domain of the function, so I can take f of a. It exists, so f of x is the same as f of x minus f of a plus f of a. Just keep in mind what we have over here. We want to use that eventually, so we're going to build this up to get to there. All right, so it's x approaches a of f of x minus f of a plus f of a. So that's still the same. So that I'm going to rewrite as the limit as x approaches a of f of x minus f of a divided by x minus a times x minus a plus f of a. If I simplify that, I'm still left with just f of x. Now, why am I constructing it like that? Because of that highlighted section. I want to use that later. Now, why am I allowed to divide by x minus a? X is not going to be equal to a, so x minus a is non-zero. So we're looking at the limit as x approaches a, so x is not equal to a. All right, so now I'm going to dig into this limit. Now we know the limit of the product is the product of the limits provided they exist. The limit of the sum is the sum of the limit provided they exist. So we've got the limit as x approaches a of f of x is then equal to the limit as x approaches a of f of x minus f of a over x minus a times the limit as x approaches a of x minus a plus the limit as x approaches a of f of a. So that we can do provided all of these limits exist. So we're going to look at them now to see if they exist. If they exist, then I can do that. Well, what do we know? The limit as x approaches a of f of x minus f of a over x minus a, that's the highlighted one. We know that's just f's derivative in the point a, all right? The limit as x approaches a of x minus a, we can simply substitute it because that's just a linear function. So that's a minus a, so that gives me 0. Plus the limit as x approaches a of f of a. Well, I don't have to rewrite that, but let's rewrite it. So let's look at that. There's no x here, so this is just the limit of a constant, so that is just the constant. So I've shown that the limit as x approaches a of f of x is f of a. So therefore my function f is continuous at a. So if a function is differentiable, f differentiable at a implies f is continuous at a. Now I'm just using some abbreviations, just so that we see the gist of this theorem. So this theorem is very powerful. If I know f is differentiable at a point, then I can conclude it must be continuous at the point. But now if you've done logic, and if you can look at a playlist on logic if you're interested in that, if I've got a statement A implies B, if that statement is true, what do I know about the converse, the inverse, and the contrapositive? So let's look at that. Here's my theorem. What will the contrapositive of this theorem be? The contrapositive of this is if f is not continuous at A, then f is not differentiable at A. I'm using some abbreviations here. So if I know that I've got A implies B being true, a statement, then the contrapositive not B implies not A must also be true. That is all I know. I know nothing about B implies A or not A implies not B, but not B, the contrapositive, is always true if my original function is true. So that's very nice. If I can show a function is not continuous at a point, then this theorem tells me it will therefore not be differentiable. So, next question, is this true? A continuous function, if it's continuous, then it's differentiable. Let's go back to my statement. My theorem says if it's differentiable, then it's continuous. That doesn't say if it's continuous, it has to be differentiable. We don't know about that. We can't say anything about that. And a continuous function is differentiable, and that's false. Some of them could be, but a general statement, not true. For example, let f of x be the absolute value of x. A very simple example. We've got the absolute value of x. At x equal to 0, f is continuous. F is not differentiable. And we looked at that when we looked at differentiation. So at a sharp point, at a cusp point, a function is not differentiable. And we can show that with the definition of the derivative, but this is just to show that this theorem, you must watch out how you use it, that you go in the right direction. So if f is differentiable, then it's continuous. But if it's continuous, it doesn't mean it is differentiable. And that's how differentiability and continuity are linked. So it's a very powerful theorem that we can use.